In this video, I want to look at the idea of orthogonal projections. In many applications, it's necessary to decompose a vector u into a sum of two terms. One that's a scalar multiple of some specified non-zero vector A, the other being orthogonal to A. So the idea, let's suppose we have two vectors u and A, whose initial points coincide at some point which I'll refer to as Q. Then the way I want to create my decomposition, I want to start by bringing a perpendicular line from the tip of U through the line A. So essentially draw this perpendicular line from A to the tip of U. And then I'm going to construct a vector, which I'm going to call W1, that goes from Q, from this tip, to where these points intersect, where this vertical line intersects A. And then I'm going to construct a vector W2, which is U minus W1, so that both of these add up to be U. And so the idea is that W1 plus W2 is going to be equal to W1 plus U minus W1, which just simplifies to U. So I have now decomposed U into a sum of two vectors. One that's a scalar of my multiple A, and the other one, W2, is actually going to be orthogonal to A. So we can expand this idea to what's known as the projection theorem. The projection theorem says that if U and A are vectors in Rn with A not equal to the zero vector, then U can be expressed in exactly one way of the form U equal to W1 plus W2, where W1 is a scalar multiple of A and W2 is orthogonal to A. So let's look at how we can actually go about doing this. W1 is commonly known as the orthogonal projection of U on A, or the vector component of U along A. We typically write it like this, PROG for projection. We use a subscript of A since that's what we're projecting onto, and then of U. So it's the orthogonal projection of U along A. This is given by U dot A over the length of A squared times A. W2 is commonly referred to as the component of U orthogonal to A. And it's just U minus the projection of U onto A. So let's look at an example of this. So I have these two vectors, U and A, and I want to find the vector component of U along A and the vector component of U orthogonal to A. Well, in order to do this, I'm going to need to start with two things. First, U dot A. So we multiply things in corresponding positions. 2 times 4 minus 1 times negative 1 plus 3 times 2. And we can work that out to get 15. The second thing we're going to need is the length of A squared. So this would be 4 squared plus negative 1 squared plus 2 squared. Typically, when I take the norm, I need to square root this, but I want to square it, so we're just taking essentially A dot A. And for that, I get 21. So the projection of U along A is going to be given by 15 over 21 times my vector A. Or if I simplify this, 20 over 7, negative 5 over 7, 10 over 7. So this is the vector component of U along A. For the orthogonal component, we need to just do U minus this vector that we just found. 20 over 7, negative 5 over 7, and 10 over 7. So I have 2 minus 20 over 7. That's negative 6 over 7. Negative 1 minus 5 over 7. That's negative 2 over 7. 3 minus 10 over 7. That's 11 over 7. One final note, sometimes we're more interested in the norm of the vector component of U along A than the actual component itself. And if that's the case, if all we want is the norm, we can use the formula absolute value of U dot A over the norm of A.